All right, so if you have not already watched the video on refraction, you want to make sure you watch that before you start on this video, which is video 4 on light. So picking up here with applications of refraction. So if you've heard of fiber optics before, fiber optics are actually an application of the properties of refraction. So fiber optics, you can see up here in the corner, here's a picture of one of the fiber optic cables that's been opened up. A single fiber out of this bundle is actually about the size of a human hair. And this fiber could actually carry, as you can see here, all the internet, radio, TV broadcasts in the US at one time without any interference. Um, and this has to do with how these fibers are constructed, but also how they work. And this has to do by the fact that they work using the properties of light. So there are a large range of frequencies of light compared to frequencies, for example, of sound. So we're limited by the different frequencies of radio waves, but we have this wide range of the frequencies of light. And you may have heard of bandwidth, especially when we talk about things like the internet. This is just the carrying capacity for information of any sort of technology. And an optic fiber, like the one that's here in the picture, has a bandwidth a million times greater than a radio station frequency. So the radio station that you listen to, like 97.9 or something like that, we can actually feed a million times more information through one of these fiber optic cables than through that radio station. So this is one of the reasons why a lot of companies are moving to fiber optics. We use them not just for telecommunication and the internet, but also lighting. You may have seen some of these like at concerts or something like that. I have some little finger ones that light up, so the light travels through the fiber optic and then lights up at the end like different colors. And they're also using these in surgery now because they're very accurate and they can direct them in a very pinpoint manner. So how do these work? So the construction on a fiber optic cable is basically two main parts. Obviously, they're a little more complicated than this. So the core is what we saw in that picture before. And you see the diagram up here. The core is this yellow section, and it's almost pure silica glass. This is why fiber optic cables are kind of delicate in a way, because they are a core of glass, and they have an index of refraction of 1.6. The number isn't really important, but it's to compare to something else. So the large fibers in here are going to transmit the light via total internal reflection. So if you remember the video that you just watched on refraction, what that means is that the frequencies of light, when they go through this cable, are going to bounce on the inside of the fiber optic cable, and what they'll do is they're going to actually just reflect inside of the cable because the critical angle is going to be smaller than they would if they were escaping. You can see that there are a few that escape out, but most of it is going to be just an internal reflection down the cable, so it'll just travel down the fiber optic cable. And then there are smaller fibers that are around the outside out here on the edge of the core. Oops, sorry. That are guiding it to move it in a straight line. So why do we care about the index of refraction number? So the cladding, which you see here in the diagram, is a transparent material with a lower index of refraction, just slightly lower, 1.5 or so, but it's to help to keep the light in the core because there's that slight difference in the index of refraction. It keeps it from actually bouncing out. That's why you see so little of it lost. And in fact, fiber optics lose next to no data as they travel. This is why we've been converting to them. Very efficient as far as data information travel. Another property of refraction is one that you're probably familiar with. I'm sure you've all been driving down the road on a really hot day, and that's when you see one of these kinds of things. We call them mirages. This is caused by a bending of light by the hot air. So it is refraction, and when we talked about when you saw refraction before, it was moving from one medium to another, so air to water and so on. But here we are moving from air to air, but it's a difference in temperature. So warm air to cold air. And so you've got warm air right above the surface of the sand or the road or whatever it might be, and it bends the light up. You can see here in the diagram because you've got cooler air up above it. And so it's bending that light, and what it ends up doing is because it's bending the light, it ends up creating a reflection in the surface. And so that's why it appears, like you can see in the picture here, that there are motorcycles upside down in the road. This is why sometimes people see like water out in the desert. And it's actually just a refraction of that light off of that warm or hot air right above the surface of the sand or whatever surface it might be. It's usually sand or blacktop. And it usually looks like water. You can see here, even though it looks like motorcycles and cars, it looks like motorcycles and cars in a surface of water. The other thing that happens as far as refraction that you're familiar with is this idea. And that is, if you've ever been like at a pool or a pond and you've dropped something and you try to go and reach for it, you can never seem to quite pick it up. And it's because of refraction. So when you have your eyes above the water, what you're seeing is the light bending because of refraction and making an object appear in a different location. And so the light is actually bending to your eyes, and the fish is actually located down here. But because of that light bending or refracting, our eyes are looking at it as a straight ray, just like with a mirror. We saw those straight rays. And so it looks like the fish is actually closer to the surface and closer to you than it actually is because of that refraction in the water. You may have, if you've been at a pool, noticed that if you put your head under the water, then suddenly the object looks like where it belongs. And that's because you're no longer getting that refraction or that bend in the water. Another one is sunsets. And this is kind of a cool one, at least I think it is. And this is because the atmosphere itself is refracting the light. So you can actually go to a couple of locations here in the States and see two sunsets within about 30 seconds or so of each other. The main place you can do that here in the United States is the West Coast. So you can see actually over here in the picture, San Francisco. So what we're actually seeing when we see a sunset is that the sun has actually already dropped below the horizon. So see, here's the person, and here is the actual sun location. But it appears to us that the sun is level with us at sunset. So think about that. Whenever you see a sunset, the sun is actually lower in the sky than where it appears to us. And that's because you have a thicker section of atmosphere in front of you, and it bends the light and allows us to see the sun even though it's already dropped below the horizon. So how do you see two sunsets? The way you can do this in someplace like San Francisco is you can sit on the beach, lay down and look out across and watch the sunset, and then stand up And you'll get to see the sunset again if you do it fast enough, because you'll be able to watch it set, and just that small adjustment in your height is enough to allow that refraction to let you see most of the sunset again. All right, so those are applications of refraction. Now we're going to switch over and talk about color. So I'm actually going to put that in a separate file so that way you've got them in different sections.